Good afternoon viewers and welcome to the EduSat lecture for the science stream. Yesterday we were talking to Dr. Amit Kumar from the Department of Chemistry, Dayal Singh College, University of Delhi. He was talking to us about the second law of thermodynamics, and in his lecture he detailed about the cyclic process, the Carnot cycle, and he talked about all the general aspects of the Carnot cycle. We did a derivation for finding the efficiency of the cycle, and we used that component to study the complex cyclic systems. We will in today's lecture study about entropy and its derivation from the second law of thermodynamics. And yesterday we had laid the foundation for the Clausius inequality, and in today's lecture we will be learning more about the Clausius inequality. So over to Dr. Amit Kumar.
Thank you very much, Unnati. First of all, again, I wish very good afternoon to all the viewers to the series of chemical thermodynamics. Dear friends, today we are going to start right from where we left in our previous lecture, that was on second law of thermodynamics. As you have already been briefed about, we laid the foundation of Clausius inequality. So just let us start with this introduction where what actually is a Clausius inequality. For this, let us consider that there is a cyclic integral of a quantity called dq by t that is equal to or less than 0. It was proved in our foundation derivation for the Clausius inequality. We had taken a complex cyclic system which had a number of thermal reservoirs from which the system could exchange heat, and by virtue of that we proved that cyclic integral of all such terms dq by t would be either less than or equal to 0. It cannot be greater than 0. This is where we left. So now let us have a generalization. What for this equal to sign is what for this less than sign is. We had also seen in our previous lecture that this quantity becomes equal to 0, that is for reversible process, and this quantity would be less than 0 for an irreversible process. And when it is equal to 0, then it is the reverse, it is the heat exchanged by the system at specified temperature connecting a reversible transformation of the system. And we defined this quantity dq by t then as ds, that is differential of some state property of the system, that is entropy. So now using this equation, let us now consider another process, another transformation of a system which undergoes transformation from its initial state, let us call it state 1, to its final state, that is state 2. So this transformation from state 1 to state 2, it can follow two paths. As you can see, the path which has been shown by connecting through a red line basically represents a path which transforms the system from state 1 to state 2 irreversibly. So therefore this path corresponds, this path is basically an irreversible path. Now the same final state which the system has acquired, the state 2, could now be transformed back to state 1 using a reversible path. So what I mean to say is that there are two options for state 1 to for a system to transform from state 1 to state 2. Either it may use a reversible path or it may use an irreversible path. Now suppose that the system chooses first of all to transform itself from state 1 to state 2 through an irreversible path, and after which the system is restored back to state 1 following a reversible path. So ultimately we obtain a cyclic transformation of a system, that is the system undergoes first from a change in state from state 1 to state 2 using an irreversible path, and then follows a reversible path and returns back to state 1. This is what is the cyclic transformation of the system we have supposed. So now let us apply, if the two paths which the system traverses in traversing a path in achieving the state 2 and then coming back to state 1, if it follows two different paths, one is irreversible path and one is reversible path. So, ultimately the cycle would be an irreversible cycle. It cannot be regarded as reversible cycle. Why? Because there is one path which is irreversible in nature. So, the system has traversed in forward direction using an irreversible path and then returned back to initial state using an reversible path. So, this is what I want to stress upon. The point is that even if one step is irreversible in nature, the whole cycle would be called an irreversible cycle. So, this cycle would be an irreversible cycle. So, as we have already where we had already started with, if the cyclic transformation of a system is irreversible in nature, then the relation applies, that is cyclic integral dq by t is less than 0. This is the relation which applies for an irreversible transformation. So, therefore, on this cycle also this relation holds true. Now, this cyclic integral can be split into two integrals within limits from initial state 1 to state 2 and from again while the system returns back from state 2 to state 1. Now, as I mentioned earlier that the system from state 1 to state 2 follows an irreversible path using this red path. So, therefore, what we need to write is integral within limit state 1 to 2 dq irreversible by t, because while traversing from state 1 to state 2, system has exchanged heat with the surrounding irreversibly. That is why I have written over here dq irreversible by t. Added to this is the second term, which accounts for the reversal of the system from state 2 to state 1. So, therefore, we get integral from state 2 to state 1 dq reversible by t, because this traversing of system from state 2 to state 1 using a black path is basically a reversible path. So, therefore, I have written over here dq reversible by t. Now, this whole sum should be less than 0, because the overall system is a irreversible transformation, cyclic transformation of the system. So, therefore, now idea is that since we have these two terms, the two integrals, we can make use of the definition of entropy. The way we had defined the entropy, we had defined that it is the reversible exchange of heat at specified temperature. So, basically the second term dq reversible by t then becomes ds by the definition of entropy itself, entropy change rather to say. So, therefore, this second term, instead of writing dq reversible by t, we can substitute it with ds, that is by using the definition of entropy change. Now, this ds is the change in entropy while the system traverses from state 2 to state 1 using a reversible path, since this path is reversible. So, therefore, instead of writing a plus sign, we can interchange the limits and get a minus sign over here. When this is so, now these two terms compares the transformation of the system from same initial state to same final state, but the first portion accounts for a reversible transformation and the second portion accounts for, second term accounts for the reversible transformation of the system. And therefore, now we can take this second term to the right hand side. What we are going to have is this integral from limit state 1 to state 2 dq irreversible by t is less than integral 1 to 2 ds. Now, this is where we can put in place a concept called Clausius inequality. Now, you can say we can remove these integrals and we can compare the differentials itself. So, therefore, differential quantities ds, that is the infinitesimal change in entropy for an irreversible path, therefore, should be greater than dq irreversible by t. Now, if it is important to note over here that when we defined entropy change, we defined entropy change as the reversible exchange of heat by a system with its surrounding at specified temperature. So, it does mean that if you want to calculate entropy change for a particular transformation of a system from initial state to final state, then you should look for, while the system traverses from initial state to final state, how much is the heat the system exchanges with its surrounding and at what temperature. If you take the ratio of the two, what you are going to get is that infinitesimal change in entropy, or when you take within limits. So, within limits as finite change, you can say it is the entropy change. So, it does mean that you have to, it is important to note that if you take path into account for calculation of entropy change, then you have to put in place the reversible heat exchange. That is, if you want to evaluate, I once again repeat, if you want to evaluate entropy change using path function, that is the heat exchange, then you must take into account only that path which is which accounts for reversible transformation of the system, right. So, with that we move a little further over here. So, we have introduced a concept called Clausius inequality, according to which the change in entropy of a system for any particular change in state from initial state to final state should be greater than dq irreversible by t, and this equation is known as Clausius inequality. What is ds? Now, I ask this question, isn't it that ds equal to dq reversible by t? So, it does mean that dq reversible by t should be greater than dq irreversible by t. This is inequality. Both these are heat exchange at specified temperatures, one using reversible path, one using irreversible path. So, inequality says that the heat exchange by the system with the surrounding at specified temperature connecting a reversible path is greater than that of an irreversible path. That is what is Clausius inequality. And now, this is actually the signpost of natural change or spontaneous change. This makes a decision, this inequality makes a decision as to whether we can consider with a change, and this inequality can tell us whether the change which we have considered is spontaneous or not. For this, let us move a little further through mathematical introductions. You see, Clausius inequality we have just specified. Now, this is a fundamental requirement, as I just said. Now, the question is that what are real changes? Real changes are not the irreversible changes in nature. For example, if suppose you can consider once again, in my previous lecture I had given you an example such as shedding of leaves, dry leaves from the trees when tree blossoms and bears fruit, thereafter it sheds its leaves, and therefore it is one direction change. Now, opposite direction of change we never observe, so it means it is an irreversible transformation. Now, coming back to again that metal rod which is heated at one end, so therefore it has one end hot, one end cold. It acquires after some point of time, when it is kept in an isolated system, it acquires the uniform temperature, but nobody has seen that uniform temperature metal rod then develops two hot and cold ends. So, what I mean to say is all these are natural processes where, or even the bouncing of ball, you can see when we drop a ball from a height, then after a couple of bounces it comes to rest, but nobody has seen that a ball at rest acquires energy and then makes a jump. So, all these are basically therefore to say that these are real transformations, as I said, and these are therefore irreversible in nature, because we do not observe any opposite direction change without unaccompanied by any external agency. That is important to note. So, therefore, if it is so, what we further want to say is that we will not use this inequality as such to basically as a yardstick to decide whether a particular change is basically spontaneous or not. We need to manipulate it. We need to manipulate it in a way that we take into account the changes in only state properties of system. Why? Because here you see the ds that should be greater than dq irreversible by t. Therefore, if you want to evaluate ds, then you have to look for path functions. So, that means you have to keep monitoring the system while the system traverses from initial state to final state. So, idea is that we want to manipulate this Clausius inequality in terms of state properties of system, so that when a system undergoes a change in state, let the system undergo a change in state. All we need is state variables, the variables which are corresponding to initial state and final state. So, therefore, it means that we need not take into account how the system undergoes a change. All we need is when let the system undergo a change, let us measure those properties which are state properties only in the beginning of the transformation of system, that is at initial state, and after the transformation has been completed in the final state, right. So, how we do that? let us have a look at it. Now, we see, let us consider an isolated system. What is actually the criteria of an isolated system? Isolated system means a system which can neither exchange heat nor it can exchange work or matter, neither energy in any form or matter in any form. This is what we defined in our first lecture in the series. So, it does mean it is isolated from its surrounding, or in other words we can say that it does not have any surrounding at all which it can interact with, right. Now, if it is so, basically the main characteristic of an isolated system which we are interested in over here is that it does not exchange heat with the surrounding. If so, dq, that is the exchange of heat, infinitesimal heat in infinitesimal transformation of the system will be 0. That is, no heat will be exchanged by the system with the surrounding. In that case, dq will be equal to 0. With that, let us see how our Clausius inequality transforms. When dq irreversible here, for an irreversible transformation of the system is 0, then it means ds which is greater than dq irreversible by t. If we put dq irreversible is 0, so therefore ds is greater than 0. This is the requirement of a real change in an isolated system. It does mean, it says that, so what we have done is we have just manipulated our Clausius inequality for an isolated system. The requirement for an isolated system therefore is that the change in entropy should be greater than 0, right. So, therefore, any change in an isolated system is attended by an increase in entropy of the system. This is what we have come to the conclusion. That is, the criteria we developed as Clausius inequality for any real change or irreversible change which transformed for an isolated system as ds should be greater than 0. It does mean that for during any irreversible or spontaneous transformation of the system, the entropy should increase, or all irreversible or real changes are attended by an increase in entropy of an isolated system. The word isolated here is very important because we modified our Clausius inequality just for our isolated systems, and we would see how this modification helps us in realizing the goals for non-isolated systems also. So, therefore, the entropy of an isolated system continues to increase. It means that if suppose some irreversible transformation is going on, entropy will continuously be increasing, and the question is where the system will stop, where the transformation will stop. So, therefore, if entropy change is the deciding factor and says that the entropy will continue to increase so long as the change will continue, it does mean change will stop, the system will come to rest only at a position when the entropy acquires a maximum value. So, what we have done? We have developed the criteria of equilibrium also. That is, a system will finally attain equilibrium when it attains a maximum value of entropy, which it could. So, it does mean, so we develop two criteria for an isolated system, that in an isolated system the natural change will be observed, real changes will be observed, spontaneous changes will be observed so long as entropy will increase, and the changes will cease, the system will come to an equilibrium state when the entropy attains a maximum value. So, we developed these two criteria, these two important conditions. Now, coming over to universe. You see, universe is a perfectly isolated system. I mentioned it how it is while I discussed some isolated systems and their nature in my first lecture in the series. So, universe is a perfectly isolated system in which we observe continuously there are so many natural changes occurs. I cited several examples over here in my previous lecture, and today also I briefed about them. For example, metal rod example or tree shedding leaves example, all such. So, all these are naturally occurring processes which are continuously occurring in the system. So, what it does mean? If they are occurring in the system spontaneously, it do mean that they are continuously increasing the entropy of the system. So, the concept of entropy comes from second law of thermodynamics, and the concept of energy, basically the first law First law of thermodynamics forms the basis of concept of energy. Now, Clausius sums up the two in his most famous aphorism. What is the aphorism? That energy of the universe is constant, but its entropy is striving to increase continuously. That is what in this statement Clausius summed up the two laws of thermodynamics. Having said this, now changes in an isolated system produces effects in the system in a non-isolated system. We just talked about here is the non-isolated system. Now, we switch on our attention to non-isolated system. What happens in them? You see, whenever a system is non-isolated, it means it is undergoing some kind of changes which affects itself as well as its immediate surroundings. So, what it does mean? The system and its immediate surrounding, we can say that both of these constitute a composite isolated system, isn't it? So, when the system and its immediate surroundings do constitute a composite isolated system, then it means that taken together both the system and its surrounding, we can say now this composite system is an isolated system, and whatever the conditions, whatever the criteria for spontaneous change and for equilibrium we developed for isolated system will apply on this composite isolated system also. So, what it does mean? The change in entropy will continue to increase, will be a non-zero quantity, will be a positive quantity, so long as changes continue to occur in this natural composite isolated system. Composite isolated system, mind you, once again, composite isolated system means the system of interest and its immediate surroundings. So, therefore, it means that the total entropy of the composite isolated system must increase in order to observe a spontaneous change. It does mean that delta S system, that is the entropy change in the system, plus delta S surroundings, that is the entropy change in its immediate surroundings, the sum of two would be greater than 0. That is the criteria for a for a spontaneous process in a non-isolated system. That is it. That is, the sum of the entropy change of system and surroundings should be greater than 0. Now, we can view it. We can take one of the example here. Now, example is that you see, now you can see this is the circle which you are observing over here. We can consider it as the ball. This ball, as you can see, we had considered a bouncing of ball in our bouncing of ball example, which we said as the example of natural change. When the ball bounces and now comes to rest. So, this circle within which there are very small chemical constituents, you can see they are present in the ball. So, now this ball is rests on a floor which has these small circles represent the constituents of chemical constituents of the floor. So, therefore, what has happened is when the ball had bounced, it has transferred its kinetic energy to the in the form of thermal energy of constituent particles in the floor and had come to a rest. Now, the question is, can the same ball can observe a bounce spontaneously? Now, in order to do that, what we need to do? You see, the thermal motion of molecules may be due to vibrational motion which occurs in the solid state in the chemical constituents of the floor. Now, this thermal motion is very chaotic in nature, very random. So, it is not directional. So, therefore, if we want this ball to bounce spontaneously, all we need to do is that in large amount of thermal energy need to localize itself from the molecules, from the constituents of floor into some small number of chemical constituents which are present in the ball, because the size of the ball is small and the size of the floor is very big. So, therefore, first of all is that the thermal energy of motion of molecules within the floor should first of all localize, a large amount of thermal energy should first of all localize within the small number of chemical constituents in the ball, and then if you want that this ball too observe a bounce spontaneously, then all the chemical constituents which are having this localized energy should get a direction, and that is the upward direction, and then the ball will spontaneously move. As you can see over here, the ball here it was resting on the floor, the ball which is shown over here that has bounced from the floor, it is having all its chemical constituents in which their energies are pointing only in one direction, that is upward direction, and that is how they lift the ball. But the question is, since nobody has observed this kind of a localized energy by virtue of thermal motion of molecules is orienting itself in one direction and then producing a motion. So, therefore, idea is that although the bouncing of ball from a height, when it was dropped from a height, when it make bounces and comes to rest, this is a natural process, because what happens, the potential energy which was stored in the chemical constituents of the ball by virtue of its height had converted to, when it was released, had converted to kinetic energy, and that kinetic energy, both these energies were not random in nature, they were having a direction associated with them. Potential energy when gets converted to kinetic energy, since the ball moves in a particular direction, so that this kinetic energy was having a direction there. So, that is the direction of motion of the ball. But when it gets transferred to the chemical constituents of the floor by virtue of their thermal motion or the heat, now this energy dissipates in a it leads to a chaotic distribution of energy. That means, when the energy was there in the form of kinetic energy of ball, it was having an orientation, a direction, and when this energy, kinetic energy, transferred to constituents of floor, it turned to it become the thermal motion of molecule, which is heat, which is chaotic in nature or random in nature. So, it means what has been done during this bouncing of ball, the chaotic distribution of energy has been taken place. But now what we want, if we want the spontaneous bouncing of ball by concentrating the heat by accumulation of thermal energy from a large number of molecules of fluid to the small number of molecules of ball and getting it oriented. So, there what we want is, we want energy which is chaotically dispersed to be organized and oriented in a proper direction, which nobody has seen. So, therefore, we once again obtain one very important aspect about entropy. You see, we can say, when the ball was bounced from a height, the energy which was stored by virtue of its height, a potential energy convert to kinetic energy, both were having direction, orientation, they gets dispersed in the form of chaotic, they gets distributed in the form of chaotic distribution occurs in the form of heat. But the opposite change, that is spontaneous bouncing of ball in itself by virtue of this heat, is never observed, because we do not observe from a chaotic distribution to the organized distribution of energy. This is what we can come to know about entropy also. But when the ball was bounced by our hand, by dropping the ball, it therefore means it was a natural change, so entropy would increase. So, what it does mean, when we talk about a reverse process, in this reverse process, what is going on, that it is not spontaneous. It does mean entropy would not increase, but since the entropy is increasing in our throwing of the ball and energy is getting distributed in the form of its chaotic distribution, that is heat, we can say that entropy can be considered as can be associated with a concept called randomness. When entropy increases, we observe a spontaneous change, and when we observe a spontaneous change, here we have observed that chaotic distribution of energy is taking place. So, what it does mean? It means that this entropy change can lead to a chaotic distribution of energy. So, therefore, we can say entropy is a measure of randomness. As entropy increases, the chaotic distribution increases, or in other words, the randomness increases. That is how we say, you all would be knowing from your class 12 standard textbooks, that entropy is considered as degree of randomness. That is how we can understand about this. So, now we look for a direction of change. Basically, we come to a conclusion that entropy is regarded as degree of randomness, and as the entropy increases in the system, the chaos increases, and as the chaos increases, that is, we look for a, it mean therefore mean we should look for a change in state of a system, or a direction of change in state of a system that leads to greater chaotic dispersal of the total energy of the isolated system, and that direction then would be spontaneous. So, that is why entropy is regarded as the degree of randomness. So, now the fact of matter is, since the ball, when it was thrown, it was having potential energy, it get converted to kinetic energy and ultimately to heat, and now the same heat we cannot make use of to exhibit the bouncing of ball. So, now we can develop another aspect of entropy as is that it is that energy by virtue of its chaotic distribution that is not available for its conversion into work. That definition can also be looked into. So, three ideas about entropy which we have developed till the point of time. One is the thermodynamic definition, which says it is the reversible heat exchange by the system with its surrounding at specified temperature. Other one says it is the degree of randomness. The third one, it is the energy by virtue of whose chaotic distribution which is not available for its conversion into useful work. That way also we can look at what is entropy. So, it is basically, that is why I said in the beginning in my previous lecture that if you ask a question what is entropy, it would then be a vague question. You should look at what way it changes, what kind of interpretations you make during some natural changes, that makes the definition of entropy. Then you will know a great deal about entropy, right. Now, as we have just developed that entropy is a measure of randomness, but the question arises, plants, trees, humans, many animals which we see around, all these are very ordered structure, are not they? If they are, but all these living beings which we see around, all of these are ordered structures and all of them evolve spontaneously, naturally. So, it is a very puzzling question now. One time you say natural changes are accompanied by an increase in entropy, and now this time we observe a number of natural changes contrary to your saying. Now, we observe a number of natural changes, that is evolution, all the animals, plants, vegetation, all are so symmetric in structure, they are not random structures. So, therefore, how such symmetric structures evolution could be attended by an increase in entropy or increase in randomness, in other words to say. So, the answer to this question would be, mind you, that universe is an isolated system in which we had to consider a system of interest as these living creatures, and their immediate surroundings become their surroundings, and it is the entropy change for these living beings along with the entropy change for their surrounding should be summed up, and this total entropy for an isolated system then should be greater than 0. Now, it means that the entropy change for the system of interest means living beings, this could be negative, That is, these are ordered structure. While they evolve orderly, it does mean that they evolve with a decrease in entropy, but in order to evolve themselves, their evolution, for example, lead to a continuous much more increase in entropy of their immediate surroundings. For example, we eat food, we produce heat that is distributed chaotically in the surrounding. We eat food and discrete them in the degraded form. So only some part of it which gets stored in our body, and that is how we evolve. So therefore, although the entropy change of the system of interest that such that all living beings, entropy change while they evolve is negative, that is, during their evolution, during their evolving, the entropy decreases, but simultaneously the entropy of their immediate surroundings continue to increase much more than what the entropy decrease they exhibit during their evolving. So therefore, it does mean total change in entropy for such a universal isolated system is greater than 0. So it means the evolving of all living beings, all living creatures which are so symmetric in nature, that is also attended by increase in total entropy of the universe. That is how these are evolving of these all living beings is a spontaneous process or a natural process which occurs spontaneously. Right. Having said this, so therefore entropy is a more impalpable thing than just a quantity of heat and work. Why we are saying so? You had just seen we had given 3 different aspects of entropy. So with many practical interpretations, the question what is entropy is therefore of course a vague question. So what should be the precise questions? Precise questions should be, how does the entropy change with temperature at constant pressure? How does the entropy change with volume at constant temperature? These are the questions. Why these are the questions? Because these questions, answer to these questions makes us to understand how entropy behaves in different circumstances. That is, if pressure is constant, if temperature is constant, in those conditions, how the system is what kind of transformation system undergoes and how the entropy behaves in such circumstances. That makes us understand. If we do understand that, then we would be knowing a great deal about entropy, and then we can make predictions about system, that whether whatever the transformations of system we have envisaged, that would be spontaneous or not, that would be natural or not, all such things then we can discuss. So in order to do that, now let us look at entropy again from its thermodynamic viewpoint, that is, the change in entropy equal to dq reversible by T. Now it follows that entropy is a single valued. Now you see, we had defined it as state function, and a state function properties that it should be a single valued extensive property which should depend only on the state of system. If it should depend only on the state of system, it does mean when a system undergoes a change in state from state 2 to state 1, then in that situation the state 1 should have a fixed entropy, that is S1, and in state 2 it should have fixed entropy S2, and we should be able to find a finite change delta S that is equal to integral 1 to 2 dq reversible by T. That is what we mean by saying that entropy is a state function. If so, then since these values depend only on states, so therefore delta S is same regardless of the fact whether the process is reversible or not. It does mean that no matter whether the system traverses a irreversible path or a reversible path the change in entropy of system will be the same. But if you want to calculate it, I once again mention here, I said it earlier also, I once again should press upon this point, that if you want to calculate entropy change using path functions such as heat, then in that situation you have to look for calculation purpose only, you have to look for a reversible path. but that entropy change being calculated for a particular change in state, even for a reversible path, that will be same even if the system traverses an irreversible path. Right. Having said this, although we can make use of this thermodynamic definition of entropy to calculate entropy change using path function, but it is not practical all the time to keep track of the system. So, therefore, we need to manipulate it in terms of some state functions. Now, in order to do that, but before that we would like to further consider some transformations of the system, that is isothermal transformations. What are isothermal transformations? Constant temperature transformations. So, when temperature is kept constant, so in that situation temperature in this integral can be taken out of the integral. So, therefore, since q is a path function, so it need not be a finite value, change in finite value, that is q2 minus q1. No, it is not that. It is just q reversible by t. That is, you need to keep track of how it changes, how much change in q occurs during a transformation. So, delta is equal to q reversible by t. But now, consider this an example, that is a very good example over here, that is vaporization process at the boiling point. Now, if suppose if one liquid is confined at 1 atmosphere pressure, and therefore, the boiling point which the liquid exhibits is called its normal boiling point. Normal boiling point is the temperature at which a liquid comes in equilibrium with vapor at 1 atmosphere pressure. So, therefore, suppose such a liquid is present at its normal boiling point in a closed container. So, therefore, now in this container, if suppose you provide a thermal reservoir over here, now at a higher, infinitesimally higher temperature, then some dq amount of heat enters in the system, and using which some amount of liquid gets vaporized and increases the quantity of vapor, and the piston will move upward and its volume will increase, and finally when you provide a low temperature thermal reservoir, same quantity of heat will flow back to the surrounding, and then ultimately what will happen is that system gets restored to its initial state. So, this is this vaporization therefore is a reversible process. Now, and moreover, pressure was also kept constant because volume was continuously changing, and if so, pressure is constant. So, it means heat exchange under constant pressure condition is enthalpy change. So, now we here you can please have a look at it, that change in entropy which is q reversible by t for a finite change then becomes a change in enthalpy for the process called vaporization at its boiling point. Similarly, we can look for entropy change for vaporization, fusion, sublimation. This is how for these phase transformations we can simply calculate entropy change, and more aspects will be dealt with about these entropy changes in our subsequent lectures. Thank you very much.
Thank you, Dr. Amit Kumar, for the interesting discussion and how we can talk about entropy not just as a state but also as a path function. We will be continuing with all the processes and looking at their entropy and how to do the calculations in our next lecture. Thank you, viewers. You can go at our YouTube website and look at this lecture and leave your comments, or you can send in your emails with your queries. Thank you.